Okay, so we are going to take a look at these two acid-base equilibria. First one's first. We've got this alcohol and a negatively charged nitrogen compound, and it's in equilibrium with the products here. We're asked to determine which direction is favored. And we can clearly see that a comparison of the conjugate bases, right, which would be a comparison of this negatively charged nitrogen compound and this negatively charged oxygen compound, would indicate that we're comparing atoms that are across from one another on the periodic table. So looking at a periodic table, if you have one handy, you'll see oxygen and nitrogen are next to one another across a row of the periodic table as opposed to down a column. And so when we're comparing the conjugate bases, and the atoms, bearing the negative charge are across from each other, this is definitely going to be an argument where we're comparing the electronegativities and placing the negative charge on the most stable position, that is, on the most electronegative atom possible. So oxygen, being just to the right of nitrogen on the periodic table, of course, is more electronegative. And so that is why this is the more stable anion than the negatively charged nitrogen containing compound. Okay, and it's because, again, it's the more electronegative atom bearing the negative charge. All right, and so given that this is the more stable species, then we would expect for this reaction to proceed in the forward direction. The next example, we have sulfur and oxygen bearing negative charges. And so while I said that normally we compare electronegativities, this is a situation where you've got atoms that we're comparing that are not within the same row, not across from each other on the periodic table, but rather down or up. So within a column of the periodic table, we're comparing in a different direction on the periodic table. If we compare sulfur to oxygen, sulfur is the larger atom, it's down lower, and oxygen is above. So because we're comparing down the periodic table, up and down a column, we want to use a totally different argument here. And this, like I said, this is not the most commonly used argument, but in this case we want to compare the acids, so the acid and the conjugate acid, again, just because we're going down the periodic table. And remember that sulfur is a larger atom, and so you think about sulfur here as being a great big beach ball, whereas oxygen might just be a volleyball or a smaller ball. So because of the large nature of a sulfur, there's going to be a greater distance between the H and S in the product, and so that's going to create a very weak bond, and so we'll just say weaker than the OH bond because it's a comparison, and so what's going to happen is the weakest bond is going to break first, okay, and so the reaction is going to favor the reverse. So here we have two different situations, one in which we're comparing across the periodic table, and so we want to look at electronegativities of the conjugate bases, and the other one we are comparing atoms that are down on the periodic table, and so we use the other strategy.